Welcome to this Fidelity Pointwise tutorial where we're going to show you how to create a volume grid with minimal effort. I have in front of you the screen of Fidelity Pointwise, and as you can see, I have already loaded a file with a surface grid for half of a quadcopter ready to go for the creation of the volume grid. So what I'm going to do here is to select all my domains and go to Create Automatic Volume Mesh. This tool is going to allow me to actually create my volume grid with minimal effort from me, the user, and it's going to set up several things for me. So I'm going to enter these. As you can see, I have here two options. One is the Create Volume Mesh Boundaries, which is the one that we're going to use, and the other one is to use existing volume mesh boundaries to basically assemble your volume grid, which in Pointwise terminology is called a block. In this particular case, we're going to select the first option because I want this tool to actually create the far field for me. Once the first option is selected, I'm going to zoom out a little bit so we can see what is going on. You can see that the automatic volume mesh panel opens up on your left. And you can also see the display window. A few things are happening. First, we have around the quadcopter surface grid two boxes. One box is very tight around the quadcopter, and this is called an extend box. It is the smallest box that we can actually define that is going to actually contain the entire surface grid. The larger box that you see is actually the far field that we're going to be defining today. Now, you can also see in the display window that there are several axes going on in this particular case. Because we are defining a box as a far field, we have axes for the length, for the height, and for the width of my box. So let's take a look at what's going on the left. You can see that the automatic volume mesh tool presents three tabs: the global, boundary conditions, and the advanced tab. Please keep in mind that in this video, we're going to present a short overview of the kind of options and tools that you have in this functionality. For more details, I would recommend that you check out the Fidelity Pointwise user manual. We're going to find all the details. So we're going to start with the global tab. You can see that it has two frames. One is the far field mesh and the other one is the boundary mesh. So if we look at the first section right here, you can see the first thing you're going to define is the type of the mesh that you want to create. In our case, we're going to select this option right here that is going to allow me to define a voxel mesh. The other option here is the unstructured volume grid. So we want a voxel. The next option in line is the shape. In our case, we're interested in creating a far field in the shape of a box. So that is going to be the first option right here. You can also see that you can create a far field in the shape of a cylinder, and you can also create a far field in the shape of a sphere. Of course, depending on which option you choose for the shape is going to be the different fields that you're going to see right below those options to actually define the shape that you have selected. In our case, like I said, we're going to select the box as the shape. The next thing in line is how we want to define the center. And for these, I'm going to get a little bit closer to the extend box. And you can see that you have those yellow axes in there, as I mentioned before. In this case, the way things are set up right now, you can see that those axes actually start at the center of the geometry. If we choose this option right here as the center, you can see things are going to change a little bit, and now my yellow axes start on the sides of my extend box. And that is the option that we're actually going to use. Next in line is to define the dimensions of the box that I am creating right here. For the far field, I could define a uniform dimension for all the axes, but in my case, I'm going to define different numbers right here for the dimensions of my box. In particular, for the length, I'm going to enter 500 right here. Then for the width, I'm going to enter 300 for this example. And last but not least, for the height, I'm also going to enter 500. I'm going to zoom out a little bit so we can see nicely what is going on. A couple of things to keep in mind or note right here is the way things are right now when I actually enter a number right here for, let's say, the L1 axis, which by the way is rendered in white in the display window right now because I am in this text field. When I enter a number right here, you can see that this particular number for L2 is going to be changed automatically to match what you have in here for L1. If you don't want these two fields linked, you can check this option right here and break that linkage. In that case, what you can do is specify different numbers for the L1 and L2 axis, as you can see right there. In my case, I'm going to keep all these dimensions linked the way we have them right now. The next thing in line is the boundary mesh section. In this case, I'm going to want anisotropic cells to form a boundary layer around the surface of my quadcopter. So I'm going to change this option right here from off to geometry growth. You can see that when you choose that option, several fields are going to open up so you can actually define what kind of boundary layer you want. The first thing in line is the wall normal spacing. We're going to define a wall normal spacing here of 1 into -3. That is the spacing that you have on your first anisotropic cells as they grow off of the surface of the quadcopter in this case. The next thing is the growth rate, which I'm going to keep it in its default value of 1.2. What this number does is it indicates to Fidelity Pointwise that each subsequent anisotropic layer in your volume grid has to have a height that is 20% larger than the previous layer. Right here, you also have extrusion stop conditions. As you can see, you have a collision buffer, you have a final cell aspect ratio, max included angle set to 170 degrees, and then we also have the centroid skewness. In my case, I'm going to use all the default values that we have for these parameters, which are, by the way, based on our best practices. If you want more information about each one of these parameters, I do recommend that you actually check out the Fidelity Pointwise user manual. Next thing in line is going to be the boundary conditions tab. As you can see, Fidelity Pointwise has already defined several boundary conditions for you. We have the isotropic boundary condition, the boundary layer boundary condition, the match, symmetry, and periodic boundary conditions. You can also see that Fidelity Pointwise has already assigned several domains automatically to those boundary conditions based on what you have going on in your grid. In particular, we're looking right now at the isotropic boundary condition. So any domain that is not constrained to an underlying database surface is going to be assigned to an isotropic boundary condition, provided that is, of course, not going to be assigned to any of the other boundary conditions that we have defined. Next one in line is the boundary layer boundary condition. You can see things are color coded. So we have that strong pink color right here on the side, and the domains assigned to this boundary condition on the display window are also shown in that bright pink color. In this case, all the domains that are part of the quadcopter geometry, they're all constrained to an underlying database surface, and that is why they're all assigned to the boundary layer boundary condition automatically. The type of this boundary condition is a wall type, which means that Fidelity Pointwise is going to grow anisotropic volume cells off of these domains. Next one in line is the match boundary conditions. So any domain that is not constrained to an underlying database surface and that is adjacent to a wall domain is going to be assigned to this particular match boundary condition. In this case, we don't have any domain that fits that description, so that's why we have 0 domains assigned here. Next one is the symmetry boundary condition, and as you can see, Pointwise is already detecting that we have a symmetry in our case. We have half the quadcopter, so that symmetry domain is correctly assigned to the symmetry boundary condition. The type of this boundary condition is match, which means that that particular symmetry domain is going to be changed to match what is happening at the volume level with the growth of those anisotropic cells. The last option right here is the periodic boundary condition. We don't have any domains that are actually periodic. So basically we have 0 domains assigned to that particular boundary condition. You can click the new button and basically define new boundary conditions if you want to do so. So I could actually enter here, click new, set an appropriate type. For example, for my boundary condition, I could come here, select whatever domains I want to apply to my user-defined boundary condition, and then click the set checkbox for it. And as you can see, now I would have my particular boundary condition. In this case, we are not going to do that because Pointwise is nicely defining for us all the TRX boundary conditions, so there's nothing else for us to do here. The next tab is going to be the advanced tab. And as you can see, there are several things going on. The first thing that I want to show you is here we have a symmetry section over there. Fidelity Pointwise via this tool allows you to define 2 symmetry planes, but you can also see that there is a checkbox over there called automatic, and that one is checked on by default. What this option is saying is Fidelity Pointwise define for me what are my symmetry planes, and as you can see, things are working nicely here because my symmetry plane, my symmetry domain is nicely recognized by Fidelity Pointwise, and the boundaries of that plane are actually rendered in that green color. You could actually uncheck this option and define whatever symmetry plane you might want, but in my case, the automatic option is doing a really nice job. You have in here options for spacing controls, in particular decay and background spacing. I'm going to leave the default options that have been set based on our best practices and are appropriate for this particular grid that I am creating right now. And last but not least, you do have options for your voxel grid, which is what we are creating right now. I'm going to leave those options as they are right now, again, because they are default values based on our best practices. So that is going to work just fine. Going back to the global tab, at this point, I am ready to create the volume mesh. I'm going to click on the Create Volume Mesh button, and Fidelity Pointwise is going to assemble my volume grid, my block. My block has been assembled, and at this point, even though the block is assembled, it has no volume cells. It is actually empty. So I have to populate this volume grid with cells. So in Pointwise terminology, that is, I have to initialize this block. What I'm going to do is I'm going to check this checkbox right here. And what that is going to do is as soon as I click OK and I close the automatic volume mesh functionality, then Fidelity Pointwise is going to automatically start the initialization process. As we can see, the automatic volume mesh tool has been closed and Pointwise is already initializing my block. Fidelity Pointwise continues to do its job of initializing the volume grid. And if I zoom in a little bit closer, we can actually see those anisotropic layers growing. Don't be afraid to zoom in very, very close. You can see how the anisotropic layers are actually advancing. One thing that is going to happen once the growth of anisotropic cells stops everywhere in your grid, you're going to see that the anisotropic front is going to turn red. At that point, the rest of the volume between that red anisotropic front and your far field is going to be populated with isotropic voxel cells. All right, the volume grid at this point has been initialized. So the next thing that we have to do is to examine our volume grid to make sure that it is of the appropriate quality for our solver. So what we're going to do is select our block, make sure that the block mask is actually checked on, and we're going to use the examine tool in Fidelity Pointwise. So I'm going to click examine, and you can see that a menu opens up with all the different examine metrics that we have available in the software. Some of these metrics are going to be used with domains. Some of these metrics are going to be used with blocks. In our particular case, we're going to be interested in the maximum included angle metric. So Pointwise is going to compute this metric for my entire volume grid, and it's going to show me a scale on the left with the maximum included angle. As you can see, the maximum value is about 172.7 degrees. You can also see it right here. So this is actually a pretty good maximum included angle for a volume grid like this one. One of the things that you can actually do is, for example, click on the Enable Cutting button and inspect your grid to make sure that it is appropriate. I can define cuts in different orientations and different locations, like the X, Y, and Z location, for example. So let's see what we have. Again, we're looking here at the maximum included angle. I can see that we have right there my anisotropic cells defining that really nice boundary layer. And then, of course, I have my voxel cells right here of different target edge lengths right there and right there. And all these different levels, they're actually connected with this like zipper layer that is formed by pyramids and prisms. So once I am okay with this, I'm going to click close. And I want to show you something else. What happens if you want to improve the quality of your volume mesh even further? One thing you can do is make sure your block is selected, and we're going to enter the solver. So go to Grid, Solve, and you're now in the solver for this particular block. So if you go to the Attributes tab, you can see that there is an option right here to expand the smoothing frame. In our particular case, we're going to set a cost angle threshold of 170 degrees. What we're going to do right now is to smooth the volume grid to try to reduce the maximum included angle a little bit more. Remember that it was a little bit above 172 degrees. So I'm going to target an angle like this one to improve the quality of my block even further. So right here, I'm going to switch to the Solve tab. I'm going to enter about 10 iterations and then click on the Smooth button. What Fidelity Pointwise is going to do now is to smooth my volume grid. So it's going to look at those cells that have a maximum included angle above my threshold of 170 degrees, and it's going to move the vertices of these cells ever so slightly to improve the overall quality of those cells. After the smoother has finished, you can right here, still inside the solver for my block, I can look at the function right here, look again for the maximum included angle, and this particular tool allows you to enter the examine tool directly from here. So I'm going to select the appropriate function that I'm interested in, and then click on the examine button to enter the examine functionality once again. And as you can see right here, my maximum included angle now, the maximum value for that metric is 171.5 degrees. So basically the smoother has reduced the maximum included angle in about 1 degree. So this is a pretty nice tool if you want to further improve the quality of your volume grid. So I'm happy with that. I'm going to click close. I'm back into the solver functionality for my block. I'm going to click OK to get out of this functionality. And the last thing that I want to do is to actually set up my CA boundary conditions and then export my grid in the appropriate format. Right down here in the status bar, you can see that my current CA solver is CGNS, which is fine in this case. So I'm going to go to CA, set boundary conditions, and again, I'm going to set my CA boundary conditions right here. So I'm going to click the new button over there. The first boundary condition that I want to set is the one for the far field domains. So I'm going to set an appropriate name and I'm going to choose right here far field as the appropriate type. So next, I have to assign domains to these particular boundary conditions. So I'm going to left click on the appropriate domains to select them all. These are my far field domains. So I'm left clicking on each one of them, and I am pressing the control key to make an additive selection. So after I select all 5 of them, I'm going to click right here on the set checkbox, and you can see at this point that my domains have been assigned to the appropriate CA boundary condition. You can also see that things are actually color coded to make it a little bit easier to understand what's going on. One option that I want to show you right here that is pretty handy is the hide assigned VCs. So I'm going to click on that, and you can see that the domains that have already been assigned to a CA boundary condition are now going to be hidden to make it a little bit easier, especially in complex grids, to set up my CA boundary conditions. I'm going to define another boundary condition. In this case, it's going to be the quadcopter domains. So I'm going to enter again an appropriate name over there, and this is going to be all the domains that are part of my quadcopter. So the appropriate boundary condition type in here is going to be a wool viscous. What I'm going to do here to select all these domains is I'm going to press the Shift key. Also with the left mouse button, I'm going to create a box like this one, and because I actually have the Shift key pressed at this time, only the domains that are entirely contained inside the selection box are going to be selected when I let go. So like so. All my domains for the quadcopter have been selected, so I'm going to click again here on set, and once again you can see that now those domains, 47 of them, have been assigned to my CA boundary condition. I'm going to create last boundary condition for my symmetry domain, and just following the same procedure, I'm going to set that and set the appropriate type to symmetry plane. At this point, all my boundary conditions have been defined. I'm going to uncheck the hide option over there, and if you click every single one of them again, you can see that things are actually color coded to help you visualize what is going on. So once this is done, I'm going to hit close. And the last thing that I have to do is to actually CA export my grid in this case, CGNS format. I'm going to go to File, Export, CA. I'm going to set an appropriate name for the export file, and then simply click Save. In this case, I'm overwriting my file, so I'm going to click Yes. I'm going to use the default options right here, and then simply click OK. All right, my grid in CGNS format has been exported. As you can see in the messages window, you have information relevant to this export. You also have the location and the name of the file that you just exported. If you like this video, be sure to click the thumbs up button, subscribe to our channel for more videos like this. If you have any questions or suggestions for future videos, drop us a line down below or connect with us on LinkedIn, which is linked in the description. Thank you so much for your attention.